Just a moment. Yes, so now it should work much better, I hope. All right, so by the way, this number Z mu is actually related to the size of the conjugacy class in the symmetric group of the conjugacy class mu. So let this be a small exercise for everyone. Just right now, maybe, well, in fact, this is useful to see that this, if you consider,
yeah, I think you will use it, yes.
Yes, well, if we consider the size of C mu, do you remember what is C mu? C mu is I mean, we use it for two different things, but related ones. So we consider our symmetric group and consider all permutations with cyclic type mu, right? And we either look at this guy as the set of all those permutations or as the sum of all of them in the group algebra, right? In the group algebra, in the sample of the group algebra. But anyway, so this notation with size of C mu is just the number of permutations of cyclic type mu. Okay. So the claim is that if you it is in fact n factorial over Z mu. Can anyone review this? Is it clear what is the claim? So maybe let's do this right now as an exercise.
Yes, it's.
Can you explain this?
Yes.
Is this?
So we need to permute some things.
So suppose we have a permutation of cyclic type mu. So you can write mu1, mu2, and so on. So we have cycles of length mu1, mu2, and so on.
Yes.
And sometimes we have cycles of the same length. So here, yeah, so for instance, it can happen that mu1 is equal to mu2, right?
Yes, and it's not what I wanted to do.
No, anyway, so yeah, just say how you want it. See, I explain why. Well, anyway, just proceed how you wanted to do this.
Okay, but now I forgot.
Sorry.
Sorry, it was very simple.
So maybe let's do this on some examples. So consider some specific cyclic type in for some specific n. So let's, I don't know, say that n is 8, for instance, and write down some mu, and let's count all possible. Like this, maybe, yes. So let's try to count how many permutations of this cyclic type we have.
Yes, I wanted to write something like this. Yes, right, this is exactly. We need to write some numbers here in any order. And this will give our cyclic type. This is cycle.
This give a permutation
So
from
this will give a permutation from which is a representative of this conjugacy class, right?
Yes.
And so now we should divide it by the factor which
yes,
corresponds to the number of different representations of things.
Yes.
Yes.
Because we can permute this mu's if they are equal. And we can shift numbers in one.
Easy clear what was said. So again, if we fill this one single row table with numbers from 1 to n, if we fill it somehow, this will correspond to some permutation.
Yeah.
When we think of the numbers inside of each box as a cycle permuting, I don't know, if I put here 1 to 4, this will be a cycle 1 to 2, 2 to 4, 4 to 1, okay, and so on. In each box we consider as a cycle. So we can count all possible ways to put those numbers here. This is n factorial, right? All possible ways to put numbers there. But sometimes we will get the same permutations, right? Please, sorry, I'm just explaining what is happening. So sometimes we will get the same permutation, right? So for instance, if I put everything here in all the boxes except the first one in exactly the same way, but in the first one where I put 1 to 4, if I put 2, 4, 1, this will be the same permutation because 1 to 4 is the same cycle as 2, 4, 1, right? So we need to account for all those things, right? Please continue. So how do we count them precisely?
That's all.
No, how do we get this number?
We just look at the formula,
Yes.
and this corresponds to permutation of cycles, and this corresponds to shifting of each cycle.
Is it clear?
Cycle, shift of cycle.
So why does mj from mu factorial correspond to different ways to write one cycle?
In this line we have this number of cycles with the same length. Of length.
Of length
You
J.
use all the cycles with the same length, not
Okay.
not all the cycles. But
So suppose we have.
Yeah, I see. I was asking actually about the second factor.
Okay, but one moment. So is it clear why this factor arises? This is permuting
Cycles of the same
cycles of the same length between themselves. Yes.
Can you remind me what the mj of
And J of mu is just the number of j's inside mu. So in terms of the permutation, it's just the number of cycles of length j.
but don't we need to
Ну, просто, если у нас есть 3 цикла по 2 на 4, то мы можем
Нам представляешь, как
поделить на 3
мы же
модели.
сейчас мы должны поделить на 12.
Пока
Не,
мы
количество. Сейчас что мы можем делать? Мы можем, это есть две вещи, которые мы можем делать. Мы можем сам цикл выдвигать, это то, про что я вначале говорил.
Да,
Что 1, 2, 4, это там 2, 4, 1. Но это соответствует этому множеству. А вот этому множеству соответствует то, что вы можете еще два разных цикла одной длины переставить между собой. Yes. So is it clear why this factor appears? Please explain this factor.
It's not very clear for me.
We can independently shift each cycle. So we have this number of cycles and with j variants to shift cycle of length j.
Okay, thank you. So this is perfect. So we have done this small exercise, and now understand what is the meaning of this combinatorial factor, Z mu. So you can, in fact, directly here, instead of Z mu, write, what is it? You can write size of C mu divided by n factorial instead of 1 over Z mu. Okay?
It will be very useful.
Yeah, you can, maybe let's rewrite it right now. So you can, using this small fact, you can rewrite it as sum over size of mu equals n times lambda of mu divided by n factorial size of c mu over p mu. All right, so we have shown this. So this is how we define our sure functions. But like we also, last time we mentioned alternative, so the more common definition in terms of determinants. But we are not going to prove their equivalence. This is left as an exercise with a star in the seminar. Oh, could you share the seminar? Maybe we can do this later, but anyway. All right, so this was our definition of sure functions, and the claim was that they are in fact the sure functions defined like this. They are in fact eigenfunctions for the W2 operator, and we're going to prove this right now directly. So you can actually do this in multiple ways, and there is another way on the seminar. We will discuss another way to do this, but during the lecture right now we will prove it directly, just acting by W as a differential operator on every sure function and showing that it indeed is an eigenfunction. More precisely, if you recall from the last seminar, there we discussed the point that you can see it in the files. In the seminar, we discussed that this C mu. So by the way, yeah, maybe let's use capital C for the set of all permutations of psi type mu, and lowercase c for the sum.
How will we recognize it?
Well, not like. So anyway, recall that we have this fact that C mu, which is the sum overall. Oh, sorry. Which is the sum overall. Sum overall. Overall sigma in capital C mu sigma. So this is the element in the center of our group algebra. So there was this guy, and we said that we considered how it acts in the reducible representation lambda. So we have the lambda, rho lambda from Sn to automorphisms of the lambda. This was the reducible representation. Okay, of our symmetric group, and we said that if we consider how this element from the group algebra acts in this rho lambda, we said that in fact rho lambda of C mu is a number which is equal to size of C mu times chi lambda of mu divided by d lambda. So this is a number, just a number, a constant, times an identity operator on the lambda. We discussed this on the side. Do you remember this? So that the elements from the center of the group algebra, they act in the reducible representation. They act as constants, as operators of multiplication by a constant, as scalar multiplication operators. So identity matrix times some number. And particularly, specifically, if you consider this element from the center, then it acts multiplied by a scalar multiplication operator with this particular number. We discussed this.
It's a problem 2.
It's problem 2 from the center.
Yeah, in fact, I don't know if anyone mentioned, but we, in this Google Drive, we have recordings of this elements also.
All right. And do you remember what is this chi lambda of mu? It is the what's called the symmetric group character value, which is the value of this rho lambda on some element from the conjugacy class.
It's trace.
Trace of this guy. All right. So what we want to prove is that if we act with W2, yeah, so let's call this guy F lambda of mu. And we want to prove that W2 acting on S lambda of P is in fact F lambda of 2 times S lambda of 2. So we want to theorem that the cut-and-join operator, when acting on S lambda on this true function, it acts diagonally in the basis of true functions, so it gives you back the same sharp function with this eigenvalue equal to precisely this guy F lambda of 2.
What is 2? It's transposition.
2 is
it goes for
is the translation. It's the it's 2 1 1. So here 2, yeah.
So 2 means 2 to the power 1, 1 to the power n minus.
Yeah, 2 to the power 1, 1 to the power n minus 2. This mu of the same of this sort.
We will omit this once for the group.
Okay, is it clear? Is the statement clear here? All right, so now we want to prove it. So let's write what we have. let's switch sides actually, and let's start from the right side. So we have let's substitute what is our definition of S lambda. So we have sum over mu f lambda of 2. I will omit the ones here. Is it clear? F lambda of 2 chi chi lambda of mu over z mu of mu. Okay, here I just substituted what is S lambda using our definition in terms of symmetric group characters. Okay. Now I want to do what? I want to substitute what is z mu and what is p mu, and also I want to substitute what is chi. So I want to write that this is the same as, it is equal to sum over mu trace. Let me for now keep f lambda of 2 is just a number. Then I want to express chi as a trace using just its definition. Okay, I will write that it's trace of ID, sorry, ID v lambda times rho lambda of some h, where h here h is some element from C mu. Okay, I'm just using the definition, like we said. So
why do we need ID here?
it will be useful later. I want to. This is the same as just writing, because I mean.
What do you mean ID? What do you mean?
ID
Trace of what?
Oh, okay, I can write it. Yeah. Let me just. Let's forget about it for now. Yes.
Yeah, okay.
Just roll lambda of h and times the product over I, pi to the power mi of mu divided by I to the power mi of mu times mi of mu, etc. So here I just use the definition of what is p mu and what is z mu. Okay? Do you agree with this? So p mu is just the product.
We would move upwards to see the definition.
So recall that z mu was this guy. Just the product.
The definition of the value.
Of what?
Of the eigenvalue. The definition of the eigenvalue.
I don't need it so far.
But
what I've done here in this equality, I've substituted the definition of chi as a trace of rho lambda of h, where h is some element of mu. And then I represented p mu.
so there's nothing happened.
Nothing happened. I substituted just the definition. So chi, z, and p mu. Do you agree? So P mu is just the product of all P mu i's, but I can rewrite it as like this. As a product of all i's, P i's to the power mi mu. Mi can be 0 when we do not have when no mu i's are of length I. No mu j's are of length I. Okay? Do you agree with this?
Yeah.
So far nothing has happened. But now, what I want to say is that I can, so this is a constant, a number, I can move it inside the trace. And I can say that I can represent it as sum over mu trace of, and here I do it like this, f lambda of 2 times id d lambda, okay, times the rho lambda of h. So nothing happened. I can multiply a matrix with an identity matrix and it remains the same. And I can move this number inside the trace. And nothing happened. Okay? So we have this, you can think of this as a diagonal matrix with elements f lambda of 2, with which you multiply this matrix and take the trace afterwards, and it's the same as taking the trace and then multiply with the number, right? And times the same thing. But then I want to rewrite what I have in down here. And specifically, I want to say that it's sum over mu trace sum over all g's in C2, or you can write C2 1 and minus 2, rho lambda of G times rho lambda of H times the same thing. So while I'm finishing writing, think about this. Why is this right? So what happened here? We just basically substituted what was our f lambda of 2. F lambda of 2 was, we said that this was the this number with which in the irreducible representation lambda, we said that our element of the center of the group algebra, our element C, in this case C2, yes, the sum of all transpositions, the sum of all transpositions, we said that it acts with f lambda of 2 as a diagonal operator of scalar multiplication by the number f lambda of 2, right? But you can re-roll this definition backwards, so saying that, so this is how it acts, okay, as an identity matrix times this number. But we said that this is the action of the sum of all transpositions. So this is the sum of all transpositions. So this guy, let me write it. You can say that that this thing is the same as rho lambda of the sum of all over G in C2 G.
It,
Right.
it denotes by C2.
Yeah, which is the same as rho lambda
Just rho lambda of C2.
of C small 2. Right? And this is just the definition of f lambda of 2. So we reverted it back here. But then we obtain this thing. Okay. But then what can we say? We say that what is rho lambda of G times rho lambda of H? Can someone say?
Rho lambda of GH.
Precisely because the representation is not some map from Sn to automorphisms of Ivan, but it's a group homomorphism. And this is just a definition of a group homomorphism, of the group homomorphism. So you say that this is sum over mu raised of rho lambda of sum over G in C2 GH times the same thing. Okay? We're just using the fact that rho lambda is a group homomorphism. Does everyone agree with that? All right. But then we want to actually see what happens when we multiply some permutation H of cyclic type mu with all possible transpositions. And you actually know what happens because we discussed this when we obtained the Kaplan-John operator. So what can happen if you multiply some permutation of cyclic type mu with a transposition? And with all possible transpositions.
You apply W2.
No, well, yeah, more or less, but what I want to say is this. So let me write down the formula, and then we'll see why it is in fact correct. So this will be a large formula. Precisely, you obtain it precisely in the same way as you obtain the action of W2, just here it's in a bit different form. So sum over mu, then sum over I. Yeah, I is not ideal because I already have I out there. So maybe let's use some other now, some other K less than L. Then sum over let me write it like this, and then I will explain. So over eta belonging to Jij of mu. So what is Jij of mu is when I'm saying that eta belongs to Jij of mu, I'm saying that eta is, so if I have mu of cyclic type if I have some permutation of cyclic type mu, I'm saying that I'm joining cycles with so this Jij is the integer partition which you get after you join cycles of cycle psi and j. Okay. Well, let me write the whole formula and then we'll
You mean
discuss.
cycles of length?
Yes. Just in like in the Cartesian formula. You remember what was ij standard there. So ij times mi of mu and j of mu.
Please repeat, what is J? It's a set of what?
So Jij is in this case. So you look at some cyclic type.
Operating with X on partitions.
Yes, it acts on partitions. So it takes a partition, and then it produces a partition where it removes, where it joins cycles of length I and cycle of length j. So it removes I and j and adds I plus j.
What is eta?
So eta is this partition.
Why?
So we take all the partitions that satisfy the.
But it will be just one partition.
No, so but the sum over them. So we take the.
So it is sum over I and J, or what?
Sorry, I and j. I wanted k and l. Sorry, I want to say that it's k and l.
Why don't we write eta equals to this?
We can do this. Yes.
Okay. So it's sum of one.
Yes.
Okay.
So, do you need in the future this notation?
It will be just one element. Yes.
So do you need this notation in the future? I mean,
Not really. Just here it's a little bit, I think, easier to see if you use this notation.
but it's one element sum.
Yes. Okay. But you need to somehow understand what is this eta, and it's different in different cases. So this is just a way to explain what is this eta.
Why don't we write eta equals to this? Why we write eta is in this? I know what.
Because where will you write it? Eta equals.
Sum eta equals. I don't know why we write sum here.
No, because I mean, I am saying that this j is a set of one element, which is just one way to write.
What is written is correct.
It's
Of course
correct.
it's correct, but
It's just
it's correct to
You
write
could
every
somehow-
integer as a sum of ones. You know.
Yes. But here it's the point is just let me finish the formula and you'll see. So it's kind of eta plus sum over eta belonging to CKL. I mean k plus m and k plus l mu time lambda eta. As you can see, I want to look at what happens when I join and when I cut. And in both cases, I use eta, and you need to somehow denote what it means here and there. So how better would you do this? We want some eta, which in this case is joining KL and mu, and here it's cutting.
We can just don't write eta.
But we need this.
But we can write just JK.
You can just write like we take this factor at the point eta equals to.
Yes, you can do this. I mean,
Because it will be less confusing in that way, probably.
Can we discuss one more time what J
what is just J and C?
Yes.
So C, KL, JKL, and CKL. So JKL, it takes an integer partition mu, and then it joins lines of length K and of length L.
But we need partition mu to have those lengths.
Yes.
Otherwise, it will be zero.
Otherwise, it's zero.
Otherwise, so it's strictly speaking, it's the sum of many zeros and one.
Yes. So in fact, it can be empty. It can be an empty set or one element set. So this is why it's more useful to write. Yes, it's more useful to write it like that because it can be empty, right?
And we write that K is lower than L
Yes.
because we need only one, because otherwise we'll have two samples of.
We'll count everything 2 times.
We'll count them 2 times, but we need also to separately count when K is equal to L. So we need to count that separately.
Can't we just write that K is less or equal?
No, because the formula is a little bit different. Because when you join cycles of the same length, there is some combinatorial factor appearing, and in fact, it will look like that. It will look like some eta in J KL per mu, 1/2 K squared. So you get this 1/2 MK of mu, and then MK of mu minus 1 chi lambda of theta plus sum over eta in C KK, oh sorry, it's KK. C KK of mu K. This 1/2, it cancels with the 2. K and 2K of mu times T chi lambda. And it gets multiplied by the same thing of these.
So why is it 1/2 or what?
Just let's see how this appears. So you need to consider all possible transpositions. So you have H, which is some element of cyclic type U, and precisely as we have done when we prove the cut and join, the formula for the cut and join equation, we do it precisely in the same way. So we are interested, because here we have rho lambda, right? We're interested only in the cyclic type of the resulting element when we multiply G with H. So if H was a cyclic type U, what can happen when we multiply it with a transposition? What can be cyclic type? What can happen? It can happen that you can, if the transposition is like that its two endpoints are in two different.
Yeah, I understand everything, but I just wanted to get a brief explanation about why is it 1/2.
Why is it 1/2? Okay, it's the same 1/2 which is in the cut and join operator. You recall this there. So
why do we have MK of mu minus 1?
just let's count what happens. Suppose you have two cycles of length k. Yes. So what can happen?
So minus
When
1
you
is
join
exactly the
cycles of length k.
Yes. So if you join cycles of mk, we can take one of mk, and the other one will be one of mk minus 1.
Yes,
So
here
we can
you
check
have
cycles.
mk times ml because you need to choose your one of the cycles of length k and one of the cycles of length L, right? And here you can choose them precisely in 1/2 times mk times mk minus 1 ways. 1/2 is just the combinatorial factor. It's the number of ways to choose 2 cycles out of mk cycles of length k.
I guess.
So you choose 2 of those guys, right? And you get k squared from the fact that your permutation, your transposition can, its endpoints can end up in every place inside of those 2 cycles of length k. So this is k squared times chi lambda theta. So is this clear? This part. But you only get anything if this is non-empty. So this is why it's useful to write like I wrote, because sometimes J can be empty. Whenever you do not have 2 cycles of length k. If you do not have 2 cycles of length k, then this guy will be just empty, and you will not have a summand of this form.
And why the trace is equal to this?
It's just by the definition. So trace of rho lambda of this cyclic type jkk of mu, when you join two cycles of length k and get 1 of length 2k, this is by definition is chi lambda theta. Do you agree? So does everyone completely agree why in the specific case when when our transposition, when we count all the transpositions which joins 2 cycles of length k, you get this part of this expression. With all the other parts, you can do it precisely in the same way. So we already explained this guy is completely similar, only you get, instead of 1/2 m times m minus 1, you just get the product. So all ways to choose 1 cycle of length k and 1 cycle of length L, when they're not equal, you just mk times ml, and that's it, without any combinatorial factor. Then you get k times L because you can place the endpoints in so many ways, right? And you get chi precisely in the same way as here, just from the definition of rho lambda of theta, right? Of trace rho lambda of theta, of not theta, of GH, where GH is those cyclic type theta. Okay? And these those 2 parts, they are completely similar, only you look at what happens when you join, when you cut. So CKL is when you have, in your integer partition, when you have a k plus L, a row of length k plus L, and you divide it into 2 guys of length k and L. Yes? So it can be either, again, 1 element or empty with CKL. Is it clear? Is it clear what is this CKL to me?
Yeah.
Let's just maybe write some examples. So, what is J22 of 3 to 1? What is J22 of 3 to 1? Empty.
Does anyone agree with me that it will be more understandable if we not wrote the sum, but we wrote like the indicator if the set of this is not empty?
It looks very.
What is 3-1?
Will you really use this sum?
So if I write this article, I would have thought that I'm mistaken and I'm understanding this sum in the wrong way. It's a bad notation, I think.
Anyway, we use it as if it works, and we are using it. So, what is J31 of 3 to 1?
4 to.
It's J42. Set with 1 element 4 What is C22 of 4-1?
2, 2, and 1.
Set of 2, 2, 1. What is C22 of 3, 1? 97. So is it clear how those G, J, and C work? Anyway, so we have this formula. And
we don't need the sums because it's empty set. Then Z multiplier MK plus L will be 0.
okay.
No.
Yeah, all the m's will be zeros. Because it's a number in which cycles of length k are included in empty set.
No, okay, we need some.
Why?
So for instance, here we need.
It's okay.
So for instance, here we need it because mk. You need here 2k, so mk should be at least 2. But you have -1. Yeah, maybe you're right. But anyway, so this definition works, and we can use it. Maybe it's not a perfect definition, but it's at least it works. Anyway, now let's just look at what happens. So the claim is that this is precisely what you get if you act with. So let me maybe recall what we have here. So we have times product over all i's, pi to the power mi of mu, times I to the power mi of mu, mi of mu factorial. So, and the claim is that this is precisely what you get if you act. This is equal to 1/2 sum over KL, K plus L, PK, PL, D over D, PK plus L, plus KL, PK plus L, D over DPK, D over DPL, of sum over theta, over theta, over Z theta, theta.
I'm sorry, could you go back like a couple of rows?
Yes. I can.
One more. Bit up higher. Actually, the question is in where we change he lambda to trace.
Where?
Yeah, right here. Yeah.
Right here?
Yeah. Didn't we miss p mu?
No. So P mu is here.
But it's also p mu.
Sorry?
I p mu.
It's product of that.
Okay.
Yeah. The point is that by definition, P mu is P mu 1 times P mu 2 times and so on P mu k.
Okay.
Just the product of all mu i's and mu. Mu is the integer partition. And it's precisely, and in fact, it equals to product of overall I, pi to the power mi of mu. Because you, in this form, you look at how many ones, when I is equal to 1, you look at how many ones are in mu, and multiply and take p1 to the power of the number of ones. And this is precisely what you get here, right? Then you take a look at how many 2's are in mu, and then multiply with them. This is the same. Right, and let's look again here. So I will not do this explicit. This is just a computation. So you need to just look at what is this p eta and apply to it either this guy or that guy, right? It's cut or join. And from eta you get mu. As you can see here, eta and mu here are related in precisely the same way as you get by applying these differential operators. And you need to just count the coefficient in front of some monomial in p's. And you will see that the coefficients precisely agree if you just act with this differential operator and write it just like that. The coefficients will agree precisely. Here you get chi lambda of eta, this is the same, over z eta. Z eta you need to rewrite because here we had z mu, and z mu it differs from z eta by some factors, which you need to take into account explicitly. This is just an exercise which everyone can do. Is it clear how to do this? Look at some particular monomial p eta, act with those operators on it, and see when it is equal to p mu. And you will see that this precisely can happen if eta belongs to jkl of mu, or it belongs to ckl of mu. And consider all those cases, and the factors which you will get from the difference between z eta and z mu, which is here, and from those factors here, and from the factors which you get after applying differentiation, will be precisely these factors over here. You can check it. This is just a computation which you can do as an exercise. Okay? Is it clear to everyone how to check the last equality? You can do it by hand. Any questions? All right. So what we have proved is, and you see here that this is in fact W2. So this is equal to W2 applied to S lambda. So we have proved the theorem. And now what is left is very two small steps. Two small steps. Okay, so the first step, you recall that our H bullet was x of uw2 applied to x of p1. First thing is that we want to rewrite x of p1 in terms of sure functions, right? Because if we want to apply our theorem, we need to express the x of p1 in terms of sure functions. This we'll do on the seminar. One of the problems for the seminar is to prove some statement which will allow us to do this. I will formulate it right now, and we'll prove it during the seminar. So the precise statement is this. Proposition x of p1 is equal to sum over lambda x lambda of 1, 0, 0, and so on times s lambda of p1, p2, and so on. Overall lambda.
You claim that all P2 and so on will be cancelled.
Precisely, yes. All the PIs with I greater than 1, they will get cancelled. This will prove this on the sample. So this is how we, then we need to put it right here, right? And what do we get? So plugging our proposition into theorem, not into theorem, but into this, we get the following thing. We get that H bullet is equal to x of u w2 times sum over lambda plus lambda of 1, 0, 0 times s lambda of p. Yes? But now it's very easy to act with x of uw2. So can someone say what does this equal to? So I want to write sum over lambda. This is just a number, s lambda of 1, 0, 0, s lambda of 1, 0, 0. And what will I have here?
E to the power u f lambda of 2.
Precisely x of u f lambda of 2 times s lambda of 2. This follows from the theorem. Is it clear?
Yeah.
How do we got this? I mean, it's very easy to act with an exponential of some operator on an eigenfunction of this operator. You get just the exponential of the eigenvalue times this eigenfunction. This is trivial. So what remains is to compute somehow this f lambda of 2. And for this we need to
Yeah. Okay. So yeah, I think we can formulate.
I'll formulate the statement, which we will actually not prove in detail, but the statement is this Bychkov theorem.
Will not prove at all.
Yeah, will not prove at all. So it's Bychkov theorem.
You mean this is her?
I mean, it's the theorem is proved in Bychkov and Dershik.
But it's originally proved in just America like 20 years.
Okay. Yeah. Okay. So, in order to, I need some further definition before I do this. So, definition.
So let me remark that now we have a formula for generating series for simple Lewis numbers in terms of this true function. And but we want, the last step is we want to obtain some explicit expression for this generating series to be able to really compute it. So now it's a nice form of this generating series, but it's not. It doesn't help us to compute this H bullet. And after this last step, when we so now we how to compute this lambda, more or less now, I mean by the definition from determinants. And the last thing which we do not know how to effectively compute is this f small. And now
okay, so we need to introduce this use-Smurf element. Use-Smurf element is this sum of transpositions xk for k from 1 to n. If
so x1 is just m.
Yes. So for instance, x1 is 0. Okay.
Wait, 0?
Or
X1 is
identity.
0.
Or identity?
Identity.
X1 is
Or
0. It's 0. It's sum from 1k to k, so k minus 1k. So 1k is equal to 1. It's just an empty sum, which is 0. 0 is an element of the group algebra. We are living in the group algebra. For instance, in the group algebra, there is just a 0 element, right? The 0. So how can we represent our favorite guy, C2, in terms of UC-Smurf elements? And C2, which, if you remember, was the sum of all transpositions, how can it be represented in terms of UC-Smurf elements?
There's some.
Yes, it's their sum, so it's just x1 plus x2 plus x1 xn.
C2 from a sense.
So C2 is
So now
from
we-
Z, C, Sn. Is it clear? If we just take the sum of all UC-Smurf elements, we get all transpositions precisely where each of them is counted, is taken once, precisely once. Is it clear? Okay, so UC-Smurf elements, as you can see, they do not lie in the center of the group algebra, apart from x1. Apart from x1, they do not lie in the center. But if you take symmetric expressions, any symmetric function of UC-Smurf elements, for instance, this simplest linear symmetric function, they already do lie in the center. And the theorem is that suppose that some element y in the center can be represented as a symmetric polynomial of UC-Smurf elements. Okay, so for instance, this guy is just a linear symmetric polynomial. Yes? Suppose that some element is represented as a sum-symmetric polynomial of UC-Smurf elements. Then then we know that since it lies in the center, then rho lambda of y is equal to some y of lambda times id lambda. Right? So since capital Y is in the center, it can be represented as just a scalar multiplication operator. We discussed this already. And the statement of the theorem is that this y of lambda is equal to P of C of lambda, where C of lambda are the contents of lambda. So what are the contents of lambda?
So just the contents of the diagram. So the lambda is a partition. It has Young diagram corresponding to this partition, and contents is just contents of boxes. It's a difference between the coordinates of these boxes.
Yeah. So C box of in lambda. Sorry. If there is some box in lambda, then C box is J minus I, where J and I are the coordinates of this box in lambda. So if you have this Young diagram lambda, you have some coordinates of the boxes and
some certain coordinates. I mean,
yeah, you have, for instance, here 1, 1, it's 2, 1, 3, 1, and so on, 4, 1. Then it's 1, 2, 1, 3, 2, 2, and this is ij. So the coordinate in this case is 3, 1. And you take the difference between j and I, and it's called the content of.
But how do we evaluate P on the content? It's a single number, and we have x1.
C of lambda means that it's a tuple of contents.
Yeah. So you look at you have your P was a symmetric polynomial in X's. Okay. A symmetric polynomial.
It's just a symmetric polynomial in n variables.
It's a symmetric polynomial in n variables. Then you can plug
and you have a Young diagram of square of area n.
Yeah. So the point is that
So what do we
size of
substitute
lambda is
instead
n.
of xi?
Okay. So size of lambda is n.
Yeah. So we
So
have
then
n rows.
So no, not n rows, n boxes. You have n boxes. Size of lambda is n, it means that you have n boxes.
Okay, my question
So
is, I understand
here
everything now.
you evaluate this
Symmetric
replacing
polynomial,
xk with k's box. Xk is replaced by
Okay, I get it.
c kth box.
It doesn't
But it's
matter
symmetric. It's a symmetrical number, so the order doesn't matter. So you sum over all boxes. For each box, you have its content, and you plug
have
it.
a sum. You have a sum polynomial.
P is some symmetrical number. It's important that it's a symmetrical number.
We're absolutely not going to prove this in any way.
Yeah.
This theorem we're not going to. So in particular, this theorem,
It's, yeah.
corollary is that what is our f lambda of 2? Now you can combine those statements and obtain what is this f lambda of 2. Can someone do this? So remember that C2 was the sum of all U2-smart elements, which is the simplest non-trivial symmetrical number, the linear one, right? And precisely this number is when y is equal to C2, this is f2 of lambda. F lambda of 2, sorry.
It's a lambda 2 is just the first E1 of.
So then what does it equal
First
to? If you apply this theorem, what is it equal to? F lambda of 2. You need to plug contents into which polynomial? What is P? In the case when y is C2.
P is E1.
What is P?
First elementary symmetric polynomial.
Sum of x's.
It's sum of x's.
So
So then what do you get? What is f lambda of 2? Is it clear what I'm asking how to do this? Or you're lost? C of C box of lambda is, so suppose you have some box in lambda and it has coordinates ij. So C, the content of this box is defined by j minus I.
So it's just sum of C. Yeah?
Да.
Yes, so this is sum,
Это очень мощная теорема.
precisely, so this is sum over all boxes inside of lambda, C box of lambda, which means that it's sum over all ij in lambda, j minus I. And it can actually be computed. It's sum over, it's 1/2, sum over I, lambda I minus I plus 1/2 squared. Squared minus
Это такая очень мощная штука, да, то есть мы там
I minus 1/2.
использовали немножко теорию представлений, чтобы понять, что вот нам на самом деле нужно собственное число какого-то оператора умножения в центре групповой алгебры, а потом еще использовали эту супермощную теорему, чтобы сказать, что на самом деле мы знаем собственное число.
So in fact, I mean, this theorem is not very difficult to prove. It just we need to go a little bit deeper into the representation theory. So there you need to construct some special basis, and in this basis it will be evident. The statement you can read it up, for instance, in this Bychkov Verges paper. Okay, is the corollary clear to everyone? Because your P was just the symmetric linear polynomial, so the answer for C2, which is f lambda of 2, is equal to the sum of all contents. It's this guy. Sum over all ij belonging to your Young diagram, j minus I. And you can take the sum.
Maybe the last equality, maybe use it as an exercise.
Yeah, this we can use and show as an exercise. This is just applying the formula for arithmetic regression, right? So this equality follows from the formula for the sum of arithmetic regression, right? Because if you want to take some particular column and sum over all these guys, and we'll get this, and they are linearly rising. Okay, we'll stop here for now. So we arrived. Let me maybe just as an endpoint. So statement that H bullet is equal to sum over lambda x of sum over ij in lambda I minus j times s lambda of p
We are
times s lambda.
here because of we one time wrote j minus I, one time.
Oh, sorry, j minus I. I'm sorry, it's j minus I. J minus I. U times the sum over all I and j and lambda, j minus I. So this is the formula for our.
And it is very easy to compute. I mean, very easy to plug into the mathematics.
And why do we need this formula in this form? Because we are interested in generalizations, the monotone, Bruce numbers, and so on. And it turns out that in order to write many generalizations, you just need to put here f of this guy, some function of the content,
And it will.
and choosing particular f's will give you different types of fruit samples. We'll discuss it later. And we are interested we will be interested in the more general guy of this form, where, so for instance, here you, instead of 1, 0, 0, 0, you can also plug some numbers, and here take some function, and this will be a very general thing. In fact, this guy will see that it's this what's called half function of cadence, especially the hierarchy, and for general parameters here and there, it will be this function, and we can then prove topological recursion in general for the general form of this guy written in this way. And we'll see it in the remaining time of our course.